Okay, good day, my students. I think it's quite some time that we met. Um, we want to use this platform to cover the remaining topics. Yes, and we are going to begin with the first topic: probability. Probability. So let me begin. Probability. Probability. Okay. Now, I have, in order to use this video effectively, I have sent you a document. So we are going to go according to the document. So if you don't have it, it's not the one I sent to you earlier. The one I sent to you earlier is very detailed. That gives you self-explanatory. So the things that you may not understand here, you can go back to the notes to go and look at it. But this one is what is specifically being used together with this video. So try and get that one if you want to appreciate the video well. So let's begin. The concept of probability. Concept of probability. That is the topic that we are going to look at. So we are only going to look at the basic concept. As a business student, you just need some basic concept to help you in your business area, in finance, in accounting, in marketing, in procurement, and supply chain management. You just need it to help you in this area. Okay, so let's begin. First of all, let's start by asking ourselves what probability is all about. In fact, we are very much aware that probability in our business setting, there are a lot of risks and uncertainty, full of risks and uncertainty. If an accountant is preparing budget, he will make a lot of estimates, a lot of forecast. So, what is the chance that the forecast that he has made will actually materialize? Good. We may talk about a procurement, a supply chain manager who may think of assessing the prices at which he's going to use for his quotation. What is the probability that between the time that he made the assessment for the quotation and the time we are actually buying the item, prices has not changed? So all these are subject to risks and uncertainty. In finance, there are so many elements that are not certain. You buy shares at a certain price today, and you don't expect the price to be the same. Certain things may happen. The price may be fluctuating. And what is the probability? How will you measure the likelihood of this event occurring? So if you want to measure the likelihood of these events occurring, we use the concept of probability. So we can talk about probability dealing with measuring quantitatively the likelihood that an event may occur, or an event or an experiment will have a particular outcome. That is what probability is about. So we want to look at quantitatively the likelihood that an event or an experiment will result in a particular outcome. So we want to measure the risks that are associated with a particular event. That is what probability is about. So it is very, very well applied in insurance, risks and insurance. So when you go to those people that do life insurance, that do asset insurance, etc., they use probability a lot. So if you want to become an actuarist, or if you are doing actuarial science, this is a very powerful tool used by the actuarial scientists. Very good. So in summary here, we say that probability deals with measuring quantitatively the likelihood that an event or an experiment will have a particular outcome, or the risks that are associated with a particular event. For us to appreciate probability very well, there's a need to understand certain terms that we want to look at. So let's look at those terms. Okay. The first term we want to look at is one. I made mention of experiment. Experiment. Very good. What is an experiment in probability? Now, when we say experiment, we are talking about a process or any activity which you are interested in the outcome. So you observe the outcome. Do you get the point? So if you perform any activity or a process and you're observing the outcome of that process, so the process that you are carrying out will be referred to as an experiment. Let me give you a very funny example. When I toss a coin, so tossing the coin will be an experiment. When I toss a die, it may be an experiment. Very good. If I carry out exams right now, and I want to know your level of thinking as far as certain aspect of the course is concerned. I'm carrying out an experiment because I don't know the outcome. So every experiment, you might not know the outcome of that experiment. Experiment comes in two forms. Remember, it can be a very simple experiment that usually have a simple outcome, or you can do a multiple of experiments. So you do one, you do two, you do three in that order. So that is what we are talking about. Very good. And related to experiment is what we call trial. Trial. So what is a trial? So trial is very similar to experiment. When we perform the process once, let's call it trial. When we perform the process repeatedly under the same condition, then we have a trial. So trial will be a series of experiments that have been performed under the same condition. Good. So the key word here is the same condition. So we are performing the experiment, series of experiment, or repeated experiment, but we are doing it under the same condition. So we refer to that one as what? An experiment. Very good. When you perform an experiment or a trial, so it means now I can use them interchangeably. When I perform an experiment or a trial, then I expect an outcome. Yes, when I toss a coin, I expect that it will result in a head or a tail. Yes. So the outcome of the experiment or the trial, we refer to that one as event. So let's look at event. So that is number 3. Event. Good. So then I can say, what is an event? So event will be the outcome of an experiment or a trial. Good. So events can be the head or the tail when I toss a coin once, or a 1 or a 2 or a 6 when I toss a die, or I want to carry out an exams, you may pass or you may fail. That is an event. Any of those items, we will refer to that one as what? As events. Very good. Let's move on. Now, when you perform an experiment or a trial, and each of the event have equal chance of occurring, then we say that you are having what? An equally likely outcome. I hope you get the point. Very good. So I have a fair coin. A fair coin is a coin that is not biased. So I toss the coin. The probability that the head will occur will be the same as the probability that the tail will occur. Very good. Then lastly, let's also look at an item relating to probability. Let's call it sample space. Sample space. What is a sample space? Now, when I perform an experiment or a trial, yes, I'm looking at the possible outcomes. What are the things that are likely to come, or that are likely to occur? So all those events that are likely to occur in an experiment is known as what? The sample space. So if I toss a coin, what is a sample space? It's maybe a head or a tail. So it means that my sample space is going to be 2. So we can begin introducing some notations. Let's begin with the event. When I perform an experiment, I can be interested in the number of items that may occur in the event. We will write it like this: N of E. So N of E is the number of what? Event. Number of event. Very good. Then the number of items in the sample space, we will represent that one by N of S. So N of S becomes the number of items in the sample space, isn't it? Very good. So let's quiz ourselves a bit. Assuming I toss a fair die once, and I'm interested in even numbers. Good. Tossing a fair die once. A fair die has 6 sides. So it means that the number of possible outcome which is likely to occur when I toss it once is going to be what? 6. So N of S is going to be 6. And then I'm interested in even numbers. How many even numbers do we have from 1 to 6? Certainly 3. That is 2, 4, and 6. So it means the number of events which is likely to occur is what? Is 3. Simple as that. That's it. So in order to appreciate the concept of probability, it's very important to know these terms. experiment, trial, event, and sample space. Very good. Now that we know these terms, let's go ahead and look at how to measure probability. How to measure probability. How to measure probability. So the first thing we have done here is the basic terms. Basic terms in probability. Good. So the second thing we are going to do is how to measure. Measurement of probability. How do we measure probability? Do you remember the way we define probability? We said that probability can be viewed as measuring quantitatively. So it should be. So it means that there's a way of measuring probability in terms of quantitative approach. After all, we are doing quantitative techniques. Now, basically, there are several ways of measuring probability, but basically, three of them are usually talked about. And even among the three, we are going to concentrate on one of them. Now, the first one is to use the subjective approach. Subjective approach. The subjective approach is more or less like based on judgment, based on expert judgment. People that have knowledge in predicting the outcome of an experiment will be able to predict the situation and say, oh, the chance that this is likely to occur is that. Especially those of you that do betting. Yeah, you do betting. Probability is a very important tool when it comes to betting. So use that one there. So judgment, that is if you're using the subjective approach, is based on individual judgment. But the scientific word that we are, things should be based by empirical evidence or theoretical evidence, with theoretical evidence being stronger. So judgmental way of defining probability is usually not acceptable. The second way of defining probability is through relative or empirical approach. Now, with a relative or empirical approach, that is where we look at the number of trials which is likely to occur in a particular event over the number of times you perform that trial. Some of the examples that we'll be looking at, you will see it in there. Very good. But what we are going to concentrate much is the third way of measuring probability, that is the classical or the theoretical approach. Now, the classical approach is based on the likelihood of or the likely occurrence of the event that we are talking about. That the event that we are talking about, what is the likelihood of those events occurring? That's what we are talking about. So in this case, let's see. If we want to measure probability, basically using the classical approach, we will write probability as this. P of E. So P of E here will represent the probability of an event. And this is giving us the number of times the event is likely to occur. That's N of E. Sure, good. So N of E divided by the number of sample space. Simple as that. So probability of an event is the number of times the event is likely to occur, or the number of ways the event is likely to occur, divided by the number of sample space. So basically, this is how we are going to measure probability. Now, you know from set theory that there is no way the number of events will be more than the number of items in the sample space, because the number of events can be found in the sample space. In fact, it's a subset of the sample space. So number of events cannot exceed the sample space. The worst number of events can go is being equal to the number of sample space, isn't it? So that is this. So we can write this. We can write this. N of S. We can write this, country. Yes, so the number of events is less than or equal to the number of sample space. Yes, of course. Very good. So somebody will say, okay. So that's fine. So the definition that we have written here is subject to this condition, that N of E should be less than or equal to the number of sample space. Do you get a point? Very good. So it means the highest this value can go is number of sample space. So it means that your answer to probability can never go beyond 1. I hope you get a point. And again, the number of sample space is either 0 or more. So it means that it can never be negative. We can't say that we are interested in the boys in a particular class and then we have negative 2 boys. It doesn't make sense. So the number of events is always more than 0 but less than the sample space. Do we get the point? Let's do something here. Let's divide here by the number of sample space, here by the number of sample space, and here also by the number of sample space. Let me clean my definition from there so that you can appreciate this. Number of sample space, very good. 0 over number of sample space, of course, is going to be 0. Okay, then we can have something like this. This is the probability definition we just defined. So that is P of E. Very good. And this is 1. What does it tell you? It tells you that the definition that we gave, this definition, P of E equal to N of S over N of E over N of S, is subject to this condition that the probability of the event cannot go beyond 1 and cannot be less than 0. And this is what we call probability limit. So probability limit always ranges between 0 and 1. Perfect. Sure. Good. Okay. So now that we know this, I think we are ready to solve some few questions. So go through the document I sent to you, the document that comes together with this video, and then let's look at our first question, question 1. So I have my first question. I can't zoom the question on. You have the question, so let's go through. First question. The question reads, it says a fair die is tossed once. A fair die. A fair die have 6 sides, so you know that. What is the probability of observing a 3? A 3. Okay, so let's see how we're going to go about that. So we have a fair die. You know, a fair die have a face 1, 2, 3, 4, 5, 6. Very good. So here, what is the number of sample space? So a number of sample space is equal to 6. Very good. Then he's asking, what's the probability of observing a 3? So our event is the 3. There is only 1 3. That is this in. Very good. So our A part of the question, the probability of observing a 3. Observing a 3. Let me write it here. Oh, where's my pistol? Very good. So we can say that the probability of observing a 3 is equal to the number of events that's observing the 3 over the number of sample space. So this is going to be 1 on 6. Simple as that. Is it not simple? Very simple. Let's look at 2. The second one is probability of observing an odd number. An odd number. You know odd number. I'm not going to teach you what odd number is. So let's go through and see what the odd numbers are. 1 is an odd number, 3 is an odd number, and 5 is also an odd number. So how many odd numbers do we have in this particular case? So this is A, B. So in this particular case, the number of odd numbers is 3. So our N of E is going to be 3. So if N of E is going to be 3, then our probability of observing odd number is going to be the number of odd numbers, N of E over N of S, and this is going to be 3 on 6, and that will give you 1/2. Simple as that. Very good. Okay, then we move on. Then we go to the third part of the question. Is it a multiple of 3? A multiple of 3. Now, a multiple of 3, you know multiple of 3. 3 and then 6. Very good. So 3 on 6. So in this case, what will be our N of E? N of E, yes. N of E, yes, your guess is good as mine. That is 2. Very good. So I have 2. So in this case, try and determine the probability of getting a multiple of 3. Try. Yes. So what did you get? I got P of multiple of 3 to be N of E. N of E to be 2 out of 3. No, 2 out of 6. That's going to be 1 on 3. Simple as that. Now you could observe that in all situations, our answers were more than 0 but less than 1. That's how it works. Perfect. Let's go to the second example. That's question 2. Question 2. Now, question 2 is it determine the probability of the following events. So let's go through them. Let's see. So pick the first one. I. So is it determine the probability of the following event. So you can start. Who are you waiting for? You can't always wait for me. So begin with the I. Yes, what did you get? Okay. So it says that an even number appearing in a single toss of a fair die. I think we just did that one. Yes, we've done that one already. But that one was, the first one was an odd number. This time we have even number. So we have 1, 2, 3, 4, 5, 6. So even numbers. What are the even numbers? So our n of e will be equal to, so our n of e is 3 in this case, n of s is 6 in this case. So our probability of observing an even number becomes n of e 3 out of 6, which is 1/2. Yeah, of course, it's 1/2 because there are 3 even numbers and there are 3 odd numbers. So if you don't pick even number, you may pick an odd number. So if you are going for a bet and they say that what is the probability of picking, you decide to go for an even number, that means you have 50% chance. This is what we call 50-50, because you can express this in either fraction, decimals, etc. So this is fraction, half. So you have half chance of winning. That's what it means. Okay. Then let's go to II. What does the II says? II says that at least one head appearing in 3 tosses of a fair coin. That is, now we have fair coin, 3 of them, and then we toss them. We toss the 3 coins once. Now a coin have a head and a tail. A head and a tail. So that is 1. Now if I toss it twice, I'm going to have a head and a head, a head and a tail and a head, and a tail and a tail. So these are the possible outcomes if I toss it 2 times. So this is once and this is twice. Now if I toss it 3 times, then I have to perm it like this. So I'll have a head and then a tail in that order. Good. So in that case, I'm going to perm it. So I can have a head and a head and a head, a head and a head and a tail, a head and a tail and a head, a head and a tail and a tail, a tail and a head and a head, a tail and a head and a tail, a tail and a tail and a head, and a tail and a tail and a tail. So what is the number of sample space here? I have 1, 2, 3, 4, 5, 6, 7, 8. So in this case, my n of s is going to be 8. I hope it's clear. Very good. Yeah. So I have 8 possible outcomes. And what is the requirement? At least one head appear in 3 tours. So is it at least one head? So I am interested in those that have 1 head, 2 heads, 3 heads, etc. So this is 3 heads. 1, 2, 3, 4, 5, 6, 7. So my number of events is 7. So n of e is 7. So probability of at least a head will be 7/8. Simple. This is very simple. You can see that. Very good. So that's how it works. Then we can go to III. What does III say? It says a tail appears in the next toss of a coin if out of 100 tosses 56 were heads. This is a typical example. This is a typical situation that we use to illustrate the empirical definition of probability, that look at the number of times you've performed an experiment. So we perform an experiment 100 times, and out of the 100 times 56 resulted in heads. So it is only telling you that the probability that the next toss will result in a head, or will result in the head, will be 56/100. Yes, certainly. But you know, when you toss a queen, you may have a head or a tail. So if out of 100 tosses, in which case my number of sample space is 100. So if out of 100 tosses, 56 result in heads, then it means that 44 is going to result in tail. That's what it means. So it means my number of event here is going to be 44. So I have 44 number of event, 100 sample space. So probability of the next being a tail, next tail is going to be 44 out of 100. That is 0.44. Good. So there's a 44% chance that when you perform the experiment again, that's the 101th experiment, you will get a tail is 44%. Simple as that. Very good. The last two is for you. That is IV and V. So try that one. It says the IV says that the sum 7 appearing in a single toss of a pair of dice. A die have 6 faces. Yes. So if I toss a die twice, just like I have coin, then I have 3 coins and I toss it once. So I have 1 coin and I turn it 3 times. So a coin have either a head or a tail. So the number of possible outcome in 1 is 2. So if I toss it 3 times, it's 2 times 2 times. That's why you got 8. So it's like 2 raised to the power 3. You get a point. Good. And that gave us 8. The same applies to a die. A die have 6 faces, so 6 possible outcomes when you toss it once. And then you are tossing it twice. So raise to the power the number of times you are tossing it. And that's going to give you 36. Yeah. So in this case, this will be the number of sample space, 36. Do we get a point? And then you are interested in the sum of 7. So you either get first 1, second 6, first 2, second 5, first 3, second 3, then the first 4, second, guess for me, 2. No, it says 7, isn't it? Okay, so in this case, I'll have 4 here, and then I'm going to have 3 here, then 5, and then 2, and then 6, and then 1. So these are the possible way where the sum will be equal to 7. So I have 1, 2, 3, 4, 5, 6. 6. Yes, 6. So in this case, my N of E is going to be 6. Good. So if I want the probability that the sum is going to be 7, then it's going to be 6 over 36. So P of the sum being 37, P of sum being, okay, so let me, sum equal to 7 is going to be 6 out of 36, which is 1 over 6. Simple as that. Okay. And the last one is saying picking a picture card from a pack of 52 playing cards. You know playing cards? Those people that plays cards playing Spa. What we call Spa. If you take a Spa is divided into 4. Let me say category. I think we have, I'm not a player of Spa, but let me try if I can. I think we have diamond. This is what they call Kalu. Yeah. This is Kalu. If I'm wrong, forgive me. And then we have spade. You know spade. Spade looks like this. I'm not a good drawer. Spade. And then we have hats. And then we have good clap. You usually see this on club here. This is red, this is black, and this is black. And each of these 4 have about 13 divisions. They have 2, 3, 4, 5, 6, 7, 8, 9, 10. So each of these one have a card label like this. And then they have jack, queen, king. This is what they have. Yes. And I think they have SC. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So they have SC. So this is how it looks like. So each of all these one have all these. So this 13 times 4 will give you 52. Now among all these, the element here are picture cards. Jack, queen, and king. They are all picture cards. So go and buy a playing cards and look at it. All these are picture cards. So if you are talking about picture card, how many picture cards are there? There are 3 for one category times 4. So that will be 12. So there are 12 picture cards in the 52. So it means the number of event here is going to be 12. And the number of sample space is going to be 52. So if you are looking at picking a picture card from a pack of 52 cards, then the probability of picture card is equal to 12 on 52. Simple. That's all. Okay. So that's how it works. And in all situations, you notice that our probabilities were between 0 and 1. 0 and 1. Okay. Now let's learn about some rules in probabilities. So now we have been able to learn how to measure probability. So let's go to the third item. So the first item was the basic probability principle. The second item was the first item was some basic terms in probability. The second item was measuring probability. 3. So the third item we are looking at is looking at complements of an event. Now when we learn Venn diagram, you learn it somewhere before coming here. We learn about complement of a set. And when we say complement of a set, we are talking about elements that cannot be found in that particular set, but they are in the sample space. Yeah, it seems you've missed my face. So elements that are in the sample space but cannot be found in the event, they are referred to as the complement. Very good. Let's represent complement of an event. I still have to get up. Let's represent the complement of an event like this. So E prime. So E prime is the complement of the event E. Very good. So in probability, what happens is that an event may or may not occur. Do you get a point? So it will mean that probability of an event not occurring plus the probability of the event occurring is always certain, because 1 represents certainty and 0 represents impossible. Okay, so if I know the probability of an event, then certainly I can get its complement. The probability that it will not occur. So it means that probability of the complement of an event is equal to 1 minus probability of the event. So this is called the complementary rule. So complementary rule is saying that probability of an event not occurring is always equal to 1 minus the probability that the event occurs. Isn't that simple? Very simple. Very, very, very simple. Look at question 3. So question 3 is saying that a housing survey conducted in Accra revealed that of the random of 6,450. Okay. So what is happening here? I have my sample space, n of s being equal to a sample of 6,450. Wow. Families. 4,250 own homes, and the rest do not have homes. Okay, so those that have homes are 4,250, isn't it? Yes. What is the probability that a selected family from the sample do not have home? So they gave us those that have home. Okay, somebody may say that, well, let me find so they've given me n of each, so I can find p of each, can't I? Yes, you can, which will be number of event 4250 over the number of sample space 6450. Your calculator can do this job. I think I have my calculator here. So I will have 4250 divided by 6450. So that gives me approximately 0.659. Okay, so there's 65.9% chance that a family selected from that survey will have a home. So, but we are interested in probability of the family not having a home. So we have P of H prime, which will be equal to 1 minus P of H using the complementary rule, which will be equal to 1 minus 0.659, isn't it? Very good. And we can do the subtraction. so that we have 1 minus my answer giving me 0.341. So the probability that a person don't have home will be equal to 34.1%. So you may generalize and say, oh, from the survey that was carried out, the probability that, or the chance that the proportion of the families that do not have home is around 34%. So this can be very important for policy decisions. So that is what probability helps us to do. Okay, so that's how is it. And so you can do question 4 with this. Question 4 is for you. I'm not going to tackle that. He says that what is the probability of drawing a non-picture card from a pack of 52 cards? We learned the picture cards. I think the picture cards was 12 over 52. So if you are talking about non-picture card, it's simply 1 minus 12 over 52. This is very simple. So you can work that one out. So, but I think I've given you the answer. It's 1 minus 12 over 52. So that is what we are talking about there. Let's move on. The next item that we want to look at is intersecting events. Intersecting events. So that is 4. So number 4. The 4th item. Intersecting or partially overlapping events. So intersecting or partially overlapping events. Now, you could sometime notice that we may have events, 2 or more events, and the events are said that they have something in common. They intersect. They share some common features. In Venn diagram, we used to have this. This is an event. Let's say this event A, and this is also an event. This event B. Do you get a point? So these are sample space. Very good. So we can look at some features of this diagram. Yes, you remember this diagram somewhere. So in this case, this section, or let me begin with the whole circle. So the whole circle is A, the whole circle here is B. You and me knows that the middle here is A intersection B, isn't it? Yes, we are very much aware of that. So these are the elements that belong to both A and B. So they have some features of A, they also have some features of B. Then these are elements that belongs to A but not B. In our core mathematics, we used to call it A only. Yeah, A only. Yes, A only, but we are going to refer to it as A intersection B complement. So that's those that are in A but not in B. Do you get a point? So if that's the case, then this will be A complement intersection B, isn't it? Yes, that's how it's going to be. Okay, but so you will notice that A will have this plus that. B is going to have this plus that. Do you get a point? Very good. And if I combine this is going to be union. So everything here is going to be A union B. Yeah, we know of this one. So what about those that are in the box but they cannot be found in the circle? So they are complements, isn't it? So we can say they are A union B complements. A union B complements. So A union B or complements. And we can expand this, you know that, but we don't want to go there. We are not doing set theory, so we don't want to complicate things for you. But we can learn some few things out of this. So let's see. The first thing we can learn is this. One, that we are going to turn all of them to probability. So note them. So the first one is that the probability of event A, just event A, will be the probability of events A intersection B complement plus P of A intersection B. So you should know this. Yes. We will talk about this. We usually call this one as total probability. Total probability. So it's this plus that. That's how is it. Then again, 2, P of B will be equal to probability of A complement intersection B plus P of A intersection B. That is this plus that. This plus that. Very good. That's perfect. Again, we can define the union in terms of these three, but we can work them out, but it's not necessary we pick them from that or derive it. Number 3, you can say that the probability of A union B will have been this plus this plus this. Yes, it will have been that. So it means that I will have to pick this, and pick that, and sum them. But it is very easier to work with the total probabilities, so that we could say that probability of A plus probability of B. But you know, A have some intersection there, B also have intersection there. So when we pick them, pick A and pick B, we are counting this twice, and that is going to lead to double counting. So we must take one out. So taking one out, we have P of A intersection B. So this is what we are going to have, and this is what we refer to as the addition law of probability. Addition law of probability. So we call this one as addition law of probability. So note that it is P of A plus P of B minus P of A intersection B. But don't forget about these probability. These probabilities, they are also very, very important that you get to know of them. Yes. Okay. That is very, very, very interesting. Having known that, we can apply it. So applying it, go to question 5. Good. I hope you are there. Question 5. Okay. So question 5, it says in a survey, 500 people were interviewed. Good. That's our sample space, 500. 75 claim they had never married or given birth. Whoa. They have never married nor given birth. Okay. 345 had married. 245 had given birth. A person is chosen at random from this group. Find the probability that the person is married or blah, blah. Okay, so let's see how these rules can help us. Okay. So we begin. What have we been given? First, we have been given our sample space. Yes. So N of S here is 500. Perfect. And then it says that 75 claim they had never married nor given birth. So they are neither in the two sets, married or giving birth. So they are complement. So we could say that if you use married and M for married and G for giving birth, then we can write this one as the number of people who are married or giving birth. So union, giving birth, complement. Yes, because these are people who are either married or giving birth. So if you have never married or given birth, then you'll be in this group. So that is 75. Very good. And then again, 345 had married. So N of M is 345. And 245 have given birth. So N of B is 245. Okay. So what are they looking for? Say what is the probability that a person is married? So probability of person married or giving birth Good. This is what we are looking for. Remember that or is usually used to represent union in probability. So or, that's what we have. Okay, the first thing that will come into your mind is to apply the addition law of probability, isn't it? Okay, so let's try that. So in this case, we will have done P of M plus P of G minus P of M and G. So the N here is representing our intersection. Okay, what is P of M? We can get P of M here. Very good. By dividing by sample space, we can get P of G here. But can we get the intersection? That is the problem. Yes. So it means you don't have this. You don't have that. Two items are missing in one equation. it will be very difficult to solve for them, if possible. Unless you express one in terms of the other. So let's find a way out. We have also learned complementary rule. Do you remember? So we can write that P of M or J is equal to 1 minus P of M or J complement, isn't it? Yeah. So in this case, we are going to have 1 minus the complement. We have this guy here, 75 over 500, and that will give us something. Yes, that's going to give us something. So in this case, we have that. So use your calculator to help us. I think your calculator should be able to help us. What did you get? I don't know what you got. So in this case, I will have 75 over 500, which is 0.15. So 1 minus the answer gives me 0.85. So 0.85. So it means that 85% of the people that were involved in the survey has either gotten married or have given birth. So that is what this means. Okay, so look at the second question. It says that what is the probability that the person is married and giving birth? So this time we are looking for this and giving birth. Knowing that we have gotten this, can you see that? So what we can do is just to put this one here. We can find this from here. We can find this from there. Oh no, this is supposed to be B. Let me use B here. Good. We can find this from here, and then I've been using J throughout. So why B? Forgive me, eh? Forgive me. Okay, so J. So we can put this one here, and we can find that. So let's do that. Let's quickly do that. So in this case, we have remember when it is 1 hour, I will break it so that we can have a smaller size video, but certainly I'll continue for you. So here was 0.85, which is equal to P of M. P of M is 345 out of 500. Let me determine those probabilities here. I think that will make life easier. Yeah. So here P of M is going to be 345 over 500, isn't it? Very good. And that's going to give you, so your calculator will help us. 345 over 500 will give you 0.69, and then this one is going to give us 245 over 500, giving you 245 over 500 will give you 0.49. Very good. So we can put them in. So what is supposed to be a P of M? That is 0.69 plus P of G, 0.49. What do we need? We need P of M and G. And we can solve for this. Can't we? Take these ones, take this guy here and take this guy to the other side. So that we have P of M and G will be equal to 0.69 plus 0.49 minus 0.85. And our calculator will do the rest of the job for us. So that is 0.69 plus 0.49 minus 0.85. So give us 33%. So 0.33. What does it tell us? Out of the people that we interviewed, 33% have married and have given birth. Yes, 33 have done that. And the third one says that what is the probability that the person is married only? Married only. So married only, then we are talking about married but not giving birth. So they are married and they have not given birth. So what are we looking for? So let's go to that one. So that is I. So I, you will have probability of the person married only. So it will be and has not given birth. Yes, and we saw the definition there when I drew the Venn diagram. Do you remember? Yes, you do. Yes, you do. We can use the total probability to define that. So in that case, I will have P of so P of M married to be equal to P of M and J prime plus P of M and G. That's it. P of M and G. So this is what we have. So in that case, let's see how we are going to go about that. So this is known. Yes, it's known. It's known to be 0.69. 0.69. What are we looking for? This married only. So that is P of M and J prime plus, we have solved for this. I think we got 0.33. Yes. So the only thing we need is this, which is the question looking for. So P of M and J prime is going to be 0.69. This guy go there minus 0.33, which is equal to 0.36. So it means that 36% of the people that were involved in the survey are married only. Married only. So that is how it works. It's interesting, isn't it? Very interesting. So it works like that. It works like that. Okay. So this is a partially overlapping event. Do you know we can even extend it to 3? Yes, we can. Assuming we have 3 sets, A, B, C, and we want to find, we can write the addition law of probability for 3 events. Yes, it's possible. Let's try that. Let's try that, and then we will have to break, and then we will continue. We'll continue with the next item. That is item number 5. So in this case, I'm having A, B, and then C. So 3 events, and I can write addition law of probability for this as P of A or B or C. Let me begin with the 2, so that you learn, or it will flow from there. The 2 was P of A or B is equal to P of A plus P of B minus P of A intersection B. That's and B. Okay, so this is addition law of probability for 2 events. Let's look at 3. That would be P of A or B or C. Yes, A or B or C. So I have these 3, isn't it? So let me define it for 3 events. So I'm going to have P of A plus P of B plus P of C, just like if I define the individual items, then minus the combinations, the 2 combinations. So it will be P of A and B minus P of A and C minus P of B and C minus P of plus, because we have done the 2 possible combination. Now we are going to 3, so it's alternating. So A of P of A and B and C. Interesting, isn't it? Very good. So this is addition law for 2 sets and addition law for 3 sets. Sure. So you can try question 6. Question 6. Let me read question 6. Question 6 says that a survey is made to determine the number of households having electric appliance in Winneba. It is found that 75% have radio, 65% have electric iron, 55 have electric toaster, 50% have IR. So IR in this case is going to be iron and radio. 30% have IT. IT will be iron and toaster, and 20% have all the 3. Now find the probability that a household has at least 1 appliance. So this is what is referring to at least 1. At least 1. So this is at least A or B, at least A or B or C. So if you say that, find the probability that a household will have none of the item, then none is going to be 1 minus at least 1. Do you get a point? So that is going to be the question. So you are going to try that question for me, and then let me deal with question 7, and then so you are trying question 6 for me. In the next video which follows this, I will demand the answer to question 6. and then you will have to send your answer to question 6 either on the LMS learning system, or send it to me via WhatsApp. You can snap your solution and WhatsApp to me. Let me look at it and see whether you are correct or you are wrong. But I hope you will not be wrong. It's just a matter of applying these things. Yes, and then you I trust you. You'll be able to do it. Okay, so let's use the 5 minutes to do question 7. Then when we come, we begin with mutually exclusive event. That is where we're going to begin from. So question 7. What does question 7 talks about? Question 7 is very interesting. Now remember, in addition to question 6, I'll give you another one. Yes. So I'm going to give you 2, but I'll write that one on the board. So let's solve question 7 and I'll give you another one too for me. Question 7. What does it do? It says that given that P of x bar here will be like x prime is 2 over 3. 2 over 3. And P of y is 1/2. So P of y is 1/2. Yeah, 1/2. And P of x intersection y is 1/6. So P of x intersection y is 1/6. Now what are we looking for? P of x union y. So we want P of x union y. That is at least one of them. So this is going to be P of x from the definition that we learned plus P of y minus P of x and y and x intersection y. Very good. So we need this, but they give us the complement of it. So using the complementary rule, you know that this is 1/3, isn't it? Yes. Plus this is 1/2 and this is 1/6. And your calculator will do the rest of the job for you. Good. Let me see how my calculator sees this. My calculator seems not to have the fraction. Let me take the one that have fraction, because that one is a financial calculator. Okay, so I have 1/3 plus 1/2 minus 1/6. So that gives me 2/3. Third. So this is 2/3. Simple. So it means that probability that we have at least one of them is 2/3. None of them is going to be 1/3. Okay. Then the last one, B, 7b. Now 7b is this. It says that event A and B, for it is known that P of A is equal to 1/3 of P of B. Wow. Okay, 1/3 of P of B. So it means that P of B is 3 times A. And then P of A intersection B is 0.1. And P of A union B is 0.7. We should find P of A. Find P of A. This will be an interesting job. But for all you know, you have been given this. So we can begin from here. That P of A union B will be P of A plus P of B minus P of A intersection B, isn't it? Yes. This is known, 0.7. Yes, so you put it there. P of A is known to be 1/3. Yes, 1/3. That's P of A. It's 1/3 P of B. So it means your answer is going to be in terms of P of B. But you can work it in such a way that your answer will be in terms of P of A, isn't it? Very good. So you can leave P of A plus P of B. So instead of writing P of B, you can bring it here. So that P of B is equal to 3 P of A. 3 of P of A. Minus the intersection is 0.1. Then now you can solve for P of A, isn't it? Because that's what you're asked to find. So you can bring this one here to add up to get 0.8. And this will be 4 P of A. So that P of A will be, this will go there. So 0.8 over 4, which will be equal to 0.2. So P of A is 0.2. Simple. Okay. Now, you are going to try question 6. I'm going to end this video. It's just like left with 20 seconds. I'm going to pause this video. Yes. But you will try this question for me. for me. Together with question 6. Together with question 6. Okay, let me pick the question. I think the question is here. Where are you? Wait, I'm coming in. I'll give you the question right now. Oh, come on. It seems I can't find the question. It's quite unfortunate. Sorry. Okay. I can't find the question. But nevertheless, you were question 6 for me. If I can't find the question, I know certainly I'll find it sometime to come. The question is not upright, but work out this. Let me see. So you work question 6, and then I'll get you the second question in due course. Thank you very much. Watch out for the second video, the continuation of this.